So in this video, I wanted to just walk you through very quickly the derivation behind the distance between a point and a line formula. It's actually pretty simple based on the material that we had covered before, but I figured it would be a pretty good opportunity to kind of walk you through the process. So without looking at the rule, let's just look at the figure. Now, between the shortest distance between a point and a line would be the orthogonal orientation, if you will. All right, so what I'm going to do is kind of work off of that, but just bear in mind that we have techniques using our knowledge of vectors to help us determine the area of a parallelogram. And since a rectangle is a special form of a parallelogram, what we can do is create a rectangle out of what we have here. So I'm going to copy, paste, I'm going to draw poorly, copy, paste. All right. So we have this rectangle. Now what we can do is we can designate this. We have vector D, right? D representing distance, but it's really PM, right? Because ultimately we're looking for the value of D, all right? So we know that area ought to be base times height. So we'll just keep that in mind. So area of a rectangle is equal to base times height. All right, we also know that the area of a rectangle, area of a parallelogram, is going to be the magnitude of the cross product of two adjacent vectors. All right, so the two adjacent vectors that I'm concerned with here would be the one going from P to V, and the one going from P to M. All right, so what we can do is we could designate the vector V, just to keep it consistent with the formula, as being this vector or with an origin point of P. All right, but if you want, you can also say, well, it's going from P to V, so we can call it that. But it's really just a matter of kind of perspective, I guess. All right, so it's labeled up the way it is, so I'll use it the way it is. All right, so we'll call this PV, vector PV, and this one would be PM. Maybe I could benefit from another diagram here. That's something. All right, I'll take that as a typo bonus / Easter egg. So if somebody wants to submit that for a bonus point, that'd be fine. All right, so we know that the magnitude of the cross product of PV and PM should give us, or will give us, the area of that rectangle. All right, so what I need is just one single dimension. All right, so if I happen to know what the magnitude of each side is, now one side I do, one side I don't. All right, so this side would have a magnitude, I'll bring it in, of PM. And this one, let me shrink that down, a little shrinky dinky. And this one would have a magnitude of PV. Like I said, in theory, I would know one of the sides, maybe not the other. All right, and that's what we ended up building towards in the example that followed. But we're just working in general terms here. All right, so if I want to find base times height, and I know that that's equivalent to PV crossed against PM as a magnitude, the height, I would let that be PM. The base, I would let that be equal to PV. Sorry, this magnitude notation was kind of getting out of hand. All right, so we'd be looking at these values multiplied to give me this cross. All right, so one of them is by definition of the area of a parallelogram using the cross product's magnitude. The other is just geometry, right? But it's ultimately like a system of equations where you have two equations, two variables, multiple variables, and you set them equal to one another. All right, so if I'm looking for either PV or PM, I just divide both sides. All right, so in this case, I want to hang on to the PM. All right, so that's going to be the distance D as labeled in the diagram. If I divide out the PV, then I get D equals this guy divided by this one. And, you know, just to, again, be consistent with the formula, if I let this one be, and I'll just box it, I'll let that be V, magnitude of V. Then I would be looking at a divisor of the magnitude of V. All right. And, you know, that would require me to swap out this guy too. You know, so we would change the PM accordingly. All right, so this would also be replaced with a V, magnitude of V, so you can kind of change that on the fly, but that's entirely up to you. Yeah, the notation got a little wonky here just because of the way I kind of pigeonholed myself with the diagram, but oh, I don't need the magnitude notation there, but hopefully the theory behind it is clear. But it's pretty straightforward as dimensions of a rectangle or parallelogram being equal to the magnitude of the cross product.